All right, hello and welcome to the slides on counting, which is a topic that maybe you've seen a bit of already in like a high school class. I think I did. And so it's going to be a little bit of a review, and then also there will be some new stuff. So how do we count a bunch of random things, I guess? There's a lot to learn, so let's get started. The first things that I want to tell you about are the sum and product rules. All right, and this is only for finite things. Only for finite things. So we're counting stuff, and why not put something in a set, because we know what those are. So we're going to count things that exist in a finite set of things. So let's talk about these rules, and I think you will they will seem very familiar even though we're going to use set notation. All right, so here's the product rule. Here's what it means. Here's what it says. If there are A ways of doing one thing and B ways of doing a second thing, then there are A times B ways of performing both things. One thing from the A's and one thing from the B's. Okay? All that's saying is it's really just creating a Cartesian product of the sets. It's like, what is the size of doing all these different things, picking one thing to do out of each of these n things to do? What's the size of this set? Well, it's just equal to the size of all of the individual sets multiplied together. And to make this concrete, let me make two sets. Here is set I of all the ice cream that you could get at a store, for example. So here's vanilla, the one true flavor. Then you have chocolate, strawberry. Let's say that those are the only flavors of ice cream that are at the store. And so that's one set. And then they also have rainbow sprinkles, but nothing else. And so you have another set of options for sprinkles. You can have sprinkles, or you can not have sprinkles. No sprinkles. Okay, so that's another set. And so the product rule is saying, it's going to tell you how many different ice cream orders you could have. Well, if you have three options, right? You have three options for ice cream and two options for sprinkles. You can make a bunch of different kinds of ice cream. Like my favorite would be vanilla with sprinkles, and you can represent the exact kind of ice cream that you're going to order with an ordered pair. All right, so that's one option. You could also have like chocolate, comma, no sprinkles. There's a bunch of different options of ice cream, and every option is a member of the set I cross S. Like you pick an ice cream, pick whether you want sprinkles. How many options do you have? Well, 3 over here and 2 over here. 6 total. I hope that makes enough sense. So that's the product rule. That's all that says. Kind of self-explanatory, I hope, but yeah, they just multiply. Your options multiply. Next we have the sum rule. All right. If there are A ways of doing one thing and B ways of doing another thing, and you can't do both, then there are A plus B ways to choose something to do. That's a bit different from the product rule, where the product rule was like, you have to do one thing from A and you have to do one thing from B. Pick which ones you want. And that's why it multiplies. But with the sum rule, you just have two different sets of options, and you have to pick one from like you kind of jumble the two options together and you just pick one final thing to do. And that's essentially a union of sets. Okay? So it's like, I don't know, you could do an outdoor activity, like this is set A of outdoor activities. Like you could go hiking, you could go swimming, or you could choose from a set of indoor things to do. Maybe it's too hot out or something. You could watch a movie. You could eat dinner at a nice restaurant. I don't know. So these are like your options. It's like outdoor thing or indoor thing. Pick one. You got 4 options total. You see that? So it's a union of sets. It's like it's trying to say what is the size of a union of sets? It's just the size of each individual set added up together. Assuming there's no overlap, though. There can't be overlap. That's important. And then finally, we have the bijection rule. That's saying that if there's a bijection from one set to another, that means there's an invertible function. There's a way to move in one way and also to move back. Then that means the two sets have the same cardinality. That means the size of them are the same if there's a bijection. Okay? And so let's pretend that S and T are two finite sets. Like here's S, here's t. If there is a bijection from S to t, like I don't know what S looks like, I don't know what t looks like, but there's some bijection, like this for example is one bijection. The only way for a function to be a bijection, to be one-to-one and onto, it has to be that you're taking the same amount of things to the same amount of things. Okay? So if there's a bijection from S to t, the only way for it to be one-to-one and onto is if those sets are equal in size. Because you can't like have overlap. Like this one, like maybe there was no second thing. Like there needs to be, for it to be onto, it needs to hit everybody, for example. So hopefully that makes enough sense. If you have bijection, the sets must have the same size. So that's that. Those are all those rules. They only work for finite sets. There's infinite set rules as well. But hopefully that's a bit more concrete in your mind now. Next, let's go a bit fancier with the product rule. Let's create the generalized product rule. And so here's my silly example. Let's say that we are participating in the cat meme Olympics, and there are 15 contestants of cat memes to choose from. The question is, how many different ways are there to give out the medals to the 15 contestants? You got gold and silver and bronze to give out. And the way that you think about it is eventually you're going to build up a product, and it's going to be very similar to the product rule, but it's generalized, I guess. And so if you think about it, there's 15 people, right? And the way that you think about it is that, well, you just kind of like pick how many people could possibly get gold, for example, if that's the first medal you give out. So if you haven't picked anybody to get a medal yet, there are 15 people who could win gold without loss of generality. Let's pick this person, they get the gold. And then you have to give out silver and bronze. So do you see how there's only 14 people left to give out the silver to? I don't care who it is, but you have 14 options there. And then once you've given out gold and silver, there's only 13 people who could get the bronze. Like, I don't know, maybe this person ends up with the bronze, but there's only 13 options. And so how many different ways are there to do this? Well, it's pick 15 people, then pick 14 people, then choose from 13 people. You multiply them all together. That's how many ways you get. That's the generalized product rule. I think this is something I saw in high school, so hopefully you have too. But that's the idea. It's called the generalized product rule. It's used for counting permutations. So like we're counting all the permutations of who's going to get gold, bronze, and silver. So that's that. Here is a question for you to try now. So here is a set of some characters, and you got a bunch of different sets. You got a set of digits, a set of letters, and a set of special characters like star, ampersand, $sign. Let's pretend that users of your software have to make a password, and their passwords must include the letters from these sets only, and with an additional constraint that the user's passwords must be of length 5, 6, or 7. So they have to be 5, 6, or 7 characters long. And the characters can be special characters, digits, or letters, but the first character cannot be a letter. All right? So I want you to try to use this generalized product rule to figure out the number of passwords that satisfy this many constraints. Okay? How many passwords are there that are length 5, 6, or 7 that have their first character not a letter, but the rest of them are made up of all these different options? Okay? Think of that. Okay, so assuming you gave it a try, here's kind of what I'm thinking. Let's enumerate how many possible passwords of length 5 there are. So let's call that the length 5 set. This will be the set containing all the passwords of length 5, and we only really care about its size. So it's going to be, well, you have to pick a first character. The first character can't be a letter, so it could be a digit or a special character. And so it's essentially the first character, whatever it is, it's either a digit, so size of digits, plus size of S for special characters. So this is how many options you have for the first character, the size of the digits plus the special characters, since you can't use letters. So that's going to be our first character. That's how many we get to choose from. And then you multiply that by your choices for the rest of the characters. For your second letter, you get to choose from any of them, right? Digits, letters, special characters. So it's how many options do you have for the second character? Digits plus size of digits plus size of special characters plus size of letters. And so that's like your second character. And it's kind of the same. You keep multiplying by this for every other character, and you got 5 characters total in this set. So it's just this to the 4th power. You see that? So this is for the other 4 characters. That's the goal. And so that's the size of all the passwords that satisfy these constraints of length 5. And then you do the same for all the length 6 passwords, because you need to do, they could have any of these sizes. Length 6, size of that set. All the length 6 passwords is, well, the first character has to be a digit or a special character, so you have that many options for the first character. And then, again, you have D plus S plus L 5 more times, because it's got to be 6 characters total this time for length 6. And then the final answer is going to be the size of the length 5 set, which you could compute yourself if you'd like. Length 5 plus the size of the length 6 set, and I think you understand how to calculate the length 7 set as well. But that's how you use the generalized product rule to count something interesting, like how many passwords are allowable. What's my odds of guessing a password correctly? Things like that. So that's a good example, I hope. Here's another example. If you think about California license plates that are not customized, they're not like, they don't have spaces, or they just have random words that people choose. Every California license plate, other than the special ones, look like this. They're digit, letter, 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 digit, 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 for 7 characters total. We're eventually going to run out of digits, which is exciting. I wonder what, maybe we'll place a letter at the first spot. I really am excited to see that one day. But that's what it's like right now. How many license plate numbers are possible if no digit or letter appears more than once? So I want you to think about it like this. This is the constraint. How many license plate numbers are there if no digit or letter is allowed to appear more than once? So that's an extra constraint. Digits are totally allowed to appear, because you could have like, I don't know, 5AAA 555 as a license plate. That's valid in California, but I don't want to count that one. I want to count only the ones where everything's different. So I want a license plate that looks like 5ABC 678, all the ones that look like that. That's allowable. All right. So think about how many license plate numbers are possible if you have to only consider ones that look like this. Okay. And so again, it's going to be a use of the generalized product rule. It's going to be, well, how many options are there for digits? Like 0, 1, 2, all the way to 9, right? Those are 10 total to start with. And how many letters do you get? A, B, C, dot, 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 all the way to Z. You have 26 of those total. So, okay. Hopefully you noticed this, but let's pretend we got to choose numbers and digits in order from left to right. So the first thing we need to pick is a digit for our license plate. We're trying to count them all. How many digits are possible for the first character? Well, we haven't used any yet, so there's 10 possible. So that's 10 possibilities for the first character. And then we need a letter. We have 26 possibilities because we haven't picked any yet. We're not allowed to overlap, but we can choose any of them right now as long as we don't choose another one, the same one again. And now we multiply that by, we need to choose a second letter. But the second letter can't be the one that we picked first. So if we picked A first, we cannot use A again. So now our choices for letters is down to 25. Do you see that? Likewise, our next choice of letter, we only have 24 choices after that because we picked 2 already. We need to pick a third that's different from each of those. And then same for the last 3 digits. We need 3 digits, but we've already picked one. So we only have 9 options for this one, 8 options for the next one, 7 options for the next one. So this is the answer for all the license plate numbers that look like this, that only have no repeats. So no digit or letter appears more than once. So that's how you calculate that. So hopefully that makes a little bit of sense. Hopefully you've seen these style of problems once upon a time before. We're just going to hit them a little bit harder in this lecture. So next, let's go to permutations. A permutation, sometimes we say that there's something called an R permutation, or like a permutation with a parameter. A permutation, just in general, is a sequence that has every element of a set exactly once. That's a permutation of all the elements in the set. Okay, so for example, let's say our set is called A and it has the numbers 1, 2, 3, 4 in it. a permutation of this set is an ordered quadruple, I guess. It's take these things and put them all in some order. So like 2, 1, 3, 4 is a permutation of all the elements of set A. 3, 1, 2, 4 is also a permutation of all the elements of set A. Okay, so that's, permutations are ordered. Order matters. A permutation of the elements of A. So that's what permutations look like. And there are n factorial different permutations where if n is the size of the set. So how many permutations are there of a size 4 set? There are 4 factorial, which is equal to 4 times 3 times 2 times 1. That's how many different permutations there are of the elements of the set. That's all the different jumblings you could possibly have. Okay, so that's a permutation, and it just is like arrange every element in some order. If you just want a piece of the set and arrange those in some order, you use what's called an R permutation, and R gets replaced with a number. So an R permutation is a sequence of R things with no repetition, each thing taken from the same set. So let's see here. For example, if we still have our set A, if I want a 2 permutation, I just pick 2 things and put them in some order. So 1, 4 is a 2 permutation, we say, of the set A. Perm of the set A. Okay? And then, so are like 2, 3, that's a 2 permutation, 4, 3. It's just pick 2 things that are different from A and put them in some order. 1, 2, and you can count how many 2 permutations there are, dot, dot, dot. I think you see what's going on there. And so if you want to count how many there are, you use this kind of formula. It's PNR. It's like a function that's supposed to calculate the number of R permutations from a set with n things. So we're kind of after, if we're going to do this, if we want 2 permutations of a size 4 set, we want to calculate P for 2. Okay? And it has a formula, and I'll prove to you that it works, but like how many 2 permutations are there of a size 4 set? Well, it's like pick something to go first, that could be any of the 4 things, and then pick something to go second. There's no repeat, so you have 3 options. So it's equal to 12, but you do have a general formula for it if you don't feel like calculating it. PNR is equal to n factorial over n minus r factorial, which is, in our case, 4 factorial over, what is it, n minus r, so 4 minus 2 factorial, which is just 2 factorial, which is equal to 4 times 3 times 2 times 1 over 2 times 1, and the 2's and 1's cancel, and yes, you get 12 again. So that's just a plug and chug way to calculate that, but this is the intuition. Hopefully that makes sense. That's important. And the number of just normal permutations is you want to pick from your size of set, your set of size n, you want to pick sequences of all n things. So that's just a normal permutation at that point. That's PNN. That gets you the 4 factorial out. That's the idea. And yeah, every permutation is a tuple because order matters. Like this order matters, that 2 came before 1, 3 came before 1, and 2, things like that. So that's what a permutation is. And let's see, is that everything I wanted to say on this slide? Yes. Here is a silly example of permutations. So South Africa, a couple years ago, they had a lottery, and you can read about this on this website if you'd like, but they had a lottery and they were investigated after these numbers were drawn in that exact order, 5, 6, 7, 8, 9, and 10. There's apparently their lottery had 10 or 6 digits to draw, and there are apparently 50 balls in the lottery, and so a normal lottery number would look something like, it's just a choice of 6 numbers between 1 and 50. Like this is a possible permutation, 50, 42, 1, 8, 7, 23. That's a possible permutation of the 6 numbers that could be drawn from the lottery. But no, this one was 5, 6, 7, 8, 9, 10 in that exact order. And so the odds of that are, well, it was 1 chance over all the different ways that you could permute 6 elements out of a size 50 set, which is equal to 1 over 50 times 49 times 48, all the way to 45. And that ends up being a 1 in 11.5-ish billion chance. And so I think you can see why they were investigated at that point. But yeah, this is the 50 was the number of lottery balls total that would like end up being picked, end up being choosed from number of lottery balls. And this is how many balls to pick. So the number of balls to pick, number to pick out of that when you're calculating things. And so there's just a tiny chance that this happened, and maybe it really was legit. Who knows? There is a chance. It just is very, very unlikely. But you never know. So that's that example. Now I have a question for you. All right. So I don't know. You're a photographer at a wedding, and 10 people line up and they want to take a photo of everybody. And the bride and the groom, they're in the photo. And the question is, how many ways are there to line up those 10 people total, including the bride and groom, if the groom if we want the groom to be to the immediate left of the bride in the photo. Like we want them to be next to each other in the picture. So here is the groom, here is the bride. We want them to be in this order, but then we want to put like people, the rest of the 8 people around somewhere, like some people over here, some people over here. How many ways are there to line up these 10 people, or how many orderings are there, if the groom must be to the immediate left of the bride in the photo? All right, so think about that. See if you can come up with a number. All right, so the secret is noticing that, well, you have a bunch of different options for all these people. Like this person could be anywhere, this person could be anywhere, this person could be anywhere, except in the middle of the groom and the bride. You cannot swap these people. So like this person, treat it as a unit, put it anywhere. This person, treat it as a unit and put it anywhere. Put them anywhere. The secret for keeping and counting all the ways where the groom is next to the bride is you just count these 2 people together, count the groom and the bride in that order as a single person, because they need to be moved as a chunk. Do you see that? That's the trick. Count as one person. And so now there's really 9 entities that you can shuffle. Do you see that? There's 9 options for the first entity, maybe the bride and the groom, but maybe just a normal person. Then 8 options after you've picked where that first person goes, then 7, then 6, all the way to 1. Which is 9 factorial. There's 9 factorial orderings. And like this is like the first 9 is like at the beginning you have 9 options for who comes first. Assuming you're going to line them up. And I'm going to put who in quotes because the who might be this entity of the bride and the groom together. We cannot mix them in any other order for who comes first. That's the goal. That's the idea. So yeah, that is how you would solve that problem. And just with enough examples, I think it'll start making at least a little bit of sense. So that's that one. Let's next talk about counting subsets. That's a bit more fancy, I guess. Do you remember how many subsets of a set of a certain size there are? So like if A is a set 1, 2, 3, 4, 5, there are, you talk about the power set. That's the number. That's how many subsets. That calculates all the subsets. And then if we ask for its size, it's 2 to the power of 5. It's 32 because this is of size 5. The number of subsets is 2 to the power of the length of that set. So remember that the power set of a set, P of A, for example, is the set of all its subsets. So the empty set is a subset. The set with just 1 in it is a subset. The set with just 2 in it is a subset. And so on and so forth until like you have the set itself. 1, 2, 3, 4, 5. That works out too. Okay, so the number of subsets is 2 to the size of the original set. So there's 32 here. And the way you can think about that is like how many subsets of size 1 are there? You got the 1, 2, 3, 4, 5. Just 5 of them. And then how many subsets of size 5 are there? Well, it's just the whole set at that point. There's only one option. See that? And then, how about of size 3? How many subsets of size 3 are there? Remember that this is not a permutation because 1, 2, 3 is equal to the set 3, 2, 1. This is not a permutation. Let me draw that better. That's equal to 3, 2, 1. So we can't use the rule that we had before. This is different. This is not a through permutation. It's subsets. That's the idea. So how about a size 3? You've got 1, 2, 3, you've got 1, 2, 4, 1, 2, 5, and then you probably give up. So let's talk about this, because like it's easy for this one, it's easy for this one, this one's just weird. How do we count all the size 3 subsets of this set? How can we do it? So here, let's get concrete and try this. So you can think though that permutations kind of do it for you, even though like, if you calculate the number of permutations, that's going to include everything, but there will be some overlap. So like if you count all the size 3 permutations, like you'll get one possible permutation is 1, 4, 5. You'll get another possible permutation that's 1, 5, 4. And those are the same subset though. So like we've duplicated their count. We want to like get rid of the duplicates. But if we start with permutations, we're essentially most of the way there. That would be P53 for our particular count, our particular case of counting subsets of size 3, permutations of size 3, length 3 out of a length 5 set. And so that's going to tell us how many permutations there are of that set of length 3, but there's overcounting happening, right? So we're overcounting this twice. If you see the subset 1, 2, 3, you're going to see that a bunch of times. You're going to see 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Those are all going to appear. You see that? They all are supposed to count for the subset 1, 2, 3 though. So we overcounted it like 6 times or 5 extra times because the order doesn't matter. So we kind of have to just divide out by all of the different overlaps. So the order of our size 3 subset doesn't matter, so we end up counting each subset, because like 1, 2, 3 is a particular subset, 1, 4, 5 is a particular subset, but there's some duplicates of everything out of order when we compute the permutations. We end up counting each subset exactly, though. This rule applies, this line of thinking applies, exactly how many ways there are to reorder each of these 3 elements. So 3 factorial different ways, there's 6 times that we're going to count everything. So this chunk of 6 should really count as one subset. And all we need to do then is divide by the factorial of the size of the subset that we care about. So by 3 factorial. We're going to overcount everything 6 times, and we want to get rid of that. So the final count, how many size 3 subsets are there of a size 5 set? The answer is, first, figure out the number of permutations there are of length 3 of a size 5 set, and then divide by how many times you're overcounting each element. It's 3 factorial times. So everything's going to appear out of order that many times. Okay? We just want to count 1 for each of those 6. So divide by 6. And that comes up to 5 times 4 times 3 is the P53, and 3 factorial is 3 times 2 times 1, so the 3's cancel, and that's going to be equal to 20 over 2, so 10. There are 10 different subsets of size 3, and that's how you think about it. All right, so please yell at me if you have any questions about that. That's a weird little concept, but hopefully it makes a little bit of sense. Next up, we have combinations, and that is this idea, essentially. That's the generic way of counting subsets. You use this thing called a combination. All right, and so you end up essentially applying this function-like thing. It's called, instead of PNR, it's CNR, and that's supposed to represent the number of subsets of size R, so R subsets, or R combinations, we say, in a set with n original elements. All right, and you'll see this syntax so many different ways. Like, we cared about the number of size 3 subsets in a size 5 set, so we were trying to calculate C 5, 3, really. And there's some different notation for that. Instead of like writing it like this, you could also put it in these brackets. This is like combination notation. And so instead of CNR, you could also just write NR with some parentheses around it in this order. And you're supposed to read this as N choose R. So like you have N things, and you want R things out of that. Like you're trying to pick R things out of N things. You want all the different ways to do that, all the different subsets, because the order doesn't matter. And so the formula is, of course, PNR over R factorial. That is what we discovered here. That's the goal. And so that will simplify if you like replace this with the definition of P, the way that we did it. It ends up being N factorial over R factorial times N minus R factorial. So there is a closed form if you care, but you can totally discover this like we did up here if you forget. So yeah, we're trying to count the number of subsets, so no repetitions are allowed, so that's why we're dividing by R factorial. And so yeah, just like, similar to how every permutation is a tuple because order matters, every combination is a set because order does not matter, okay? And this is, again, something that I learned in high school. And we noticed, right, that 5 choose 3 was equal to 10, because that's how we were counting things on the previous slide. And this is a fun thing, because I think I learned this in high school, and you probably did too. But now you know what your math teachers were meaning when they said, like, they taught you combinations, and they're like, order doesn't matter. We're trying to count things where order doesn't matter. And the reason they said that is because they were trying to tell you that we are counting sets. We're counting subsets, not just permutations. But you didn't know about sets. Now you do. So that's combinations. So with that in mind, here's a question. Let's say that this is a set S. It's got 6 things in it. How many subsets of S have either 2 or 3 elements? So how many subsets of S are there where there are like 2 elements in it, like A and C, or like B and D? And then you can also, I want you to count ones that also are of size 3, so like A, C, E, B, D, E, stuff like that. So how many subsets look like this? Size 2 or size 3? How many subsets of S have either 2 or 3 elements? All right, so using combinations is definitely going to be the goal here. So see if you can figure that out. And the idea is, well, if you should just count the size 2 subsets, save that, then count the size 3 subsets separately. Add them together. That's the secret. Separately count size 2 subsets and size 3 subsets. So we have a size 6 set originally, so we have 6 things. We want to count all the ways to take size 2 subsets out of them. So 6 choose 2 plus 6 choose 3, which is going to be equal to, well, I have to pick 2 things out of a size 6 set, so 6 choices for the first thing, 5 choices for the second thing, but order doesn't matter, so I divide by 2 factorial. So that's divided by 2 times 1 for the first one, and then for this one, I'm choosing 3 things, so like 6 choices for the first thing, 5 choices for the second thing, 4 choices for the third thing, but then I overcounted. I'm choosing 3 things, so they're overcounted 3 factorial times, so 3 times 2 times 1 to get rid of those. And so this would be your final answer, assuming you did that math. So yeah, please yell at me if any of these are not making enough sense there. It's just, hopefully a lot of examples will help with this kind of thinking. It is a different way of thinking, but it is important. Next we have permutations, but this time we get to have repetitions. This is interesting. Okay, so a permutation with repetition is when you have a set of items and you want to order things. You want to find all the different ways to order things where some of those items might be identical. So, for example, you want to count all the permutations of all the letters in the string lol. That is going to trip you up because there are 2 L's. Do you see that? So that means when you're making permutations, like you're overcounting. So like, what are the characters of this? Like you're trying to, it's wrong to say that you're trying to permute a size 3 set, because there's an L, there's an O, and then there's another L. That doesn't mean anything as far as sets go. Like the L's cancel each other out. There should only be 1 L in this set. So maybe like there's an L1 and an L2. And if you're trying to compute the permutations, you'll think like L1, O, L2, you'll see that permutation. Then you'll also compute the permutation L2 first, then O, then L1. And those are not the same as far as permutations are concerned, but they're both lol, right? I hope you see the problem here. Those should be counted as 1. So some permutations are the same as others, and we shouldn't double count them. So that's no fun. How can we fix this? How can we fix this, for example? I think I'm going to show you a fancier example later, but let's see here. I guess no, let's just go to the fancy example, and then we'll do this one in full. So I will section it off so that we have room for the rest. So let's count all the ways to permute the letters in the string Beyonce. All right, so the secret is, here's the secret. Here's how you do it. You think of each letter, because like you're making a permutation, right? You're filling in letters, like who goes first, who goes second. There are 7 characters in this word, and we're trying to make a new word that is like a permuted form of it. We're trying to count every permutation of all of those letters. And so you're going to end up with 7 letters still. And so like there's 7 blanks, 4, 5, 6, 7. And the question is, you want to fill in these blanks and not double count, because you've got 2 E's, right? Those are the repeated characters. And you need to deal with those first. That's the secret, all right? So at the very beginning, you have to pick where the E's should go, because those are the duplicated characters. At the very beginning, just pick like the E should go here and the E should go here. You see that? And what you're doing when you pick where the E's should go is you're trying to come up with 2 places. Order doesn't matter. I don't care which one. Like the first E can go here and the second E can go there. It doesn't matter. I'm trying to come up with a subset. I'm trying to pick just 2 indices where to put my E's. You see that? The order doesn't matter, and that's where combinations come into play. And so that's how you can count exactly how many times you can place those 2 E's in different spots. That's the beauty of it. 7 choose 2 options to place the E's, and that's it's not going to double count because order doesn't matter with combinations. And then for the rest of the characters, you have 5 slots left to fill in. And then, like, I don't know, you have 5 characters to choose from. And so it's just 5 factorial. It's like you could put 5 options here, then you have 4 characters you could put here, 3 characters after that, then 2, and then you're kind of forced on the last one to put the remaining character there. But that is the goal. You first pick where the E's should go, where the duplicates should go. You have 2 options, and you don't want to overcount. So you pick indices, right? I want to go, they need to go at indices 2 and 5. And that's the same as indices 5 and 2. And so that's why we use combinations rather than permutations. And then the rest, you have 5 characters, and they can go in any order, so you just permute them, 5 factorial. That's the secret, okay? So with that in mind, let's figure out how to permute all the letters in LOL. You have LOL, where you don't overcount. You have LLO, and then OLL. Those are your only 3 options, I think. And the way that you can get this programmatically is think of it as you have 3 characters to fill in at indices, and then, like, I guess 1, 2, and 3. And you have 2 L's. So the idea is pick where the duplicates should go. You have 3 choose 2 spots for where those L's could go. For the L's. And then after that, after you've chosen, like, this L should go here, the 2 L's should go here, for example. Then your hand is forced at where to place the O. It's just you have 1 spot left for the O, and you have no other choice. So there's 1 spot left for the O, and you just multiply by 1 at that point because there's no choice anymore. So 3 choose 2 is the number of different ways you could permute the letters in LOL. I hope that makes sense. And that's going to give you the 3. It's like 3 choose 2 is 3 times 2 over 2 factorial, so the 2's cancel out, and it is just 3. So that is how you count permutations with repetitions. You're going to take advantage of combinations for the repeated characters so that you don't overlap. You don't duplicate the indices where you place things. It's like the first L is really the same as the second L. So that's that one. And yeah, so in general, here's the formula. You can come up with a formula for this, but hopefully it makes enough sense so far. But let me show you just a longer example, and we'll come up with this formula here. So, or there's multiple duplicates. Oh gosh. So let's scramble all the characters in Mississippi and figure out the number there. How many different ways are there to scramble all the letters of Mississippi? And we don't want to overcount with our duplicates. So how many characters are there, first of all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Gosh. So we got 11 slots to fill in. 1, 2, 3, 4, 5. Can I be lazy and make it quicker? Probably not, but I'm going to do this anyway. 10, 11 slots to fill in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so our game is, well, how many duplicates do we have here? We have 1m. That's nice. How many i's do we have? 1m. 1, 2, 3, 4 i's. How many s's? 4 s's. We have then p's, right? 2 p's. I think, does that add up to 11? Yeah. All right, so that's how many duplicates we have. And so yeah, the secret is assign a number to each character in the string and then start making choices for the duplicates first. So let's say that we'll place the i's somewhere first. We have to pick 4 slots for the i's. So it's just like, give me a subset of size 4 of these 11 choices. That's all you're asking for. That's what it means to place the i's, where order doesn't matter because they're all the same letter. See that? So to place the i's, like, could be here, then here, then here, then here, for example. How many ways are there to do that? It is, well, you have 11 slots possible, and then you want to pick 4 places, where order doesn't matter, to place those i's. They're all equivalent. So that's 11, choose 4 to start. So there's 4 i's to place. And then let's do the s's. You got 4 s's now. But we filled in 4 slots with i's. We now have only 1, 2, 3, 4, 5, 6, 7 slots to place the s's. So now we do the same game. It's like, all right, pick all the ways that you could arrange 4 s's in 7, right? Because you have 7 indices now to pick from still, to place those s's in. Do you see that? And so you're going to pick 4 of those indices in some order. Order doesn't matter. And that's where you're going to place your s's. Let's say they're there. And so there's 4 s's. And then you have to place the p's. We only have how many slots left? 1, 2, 3 slots left. We have to place the p's somewhere. And we've got 3 slots to put them in. But we have 2 p's to place. So pick 2 indices out of the 3 that are left. How many ways are there to do that? Again, order doesn't matter, so we use combination. So there's 2 p's. And then finally, once you've placed the p's somewhere, there's only 1 slot left. You have no choice anymore of where to put the m. It's got to go there. It's got to go in the empty slot. So there's only 1 slot left. You don't even have to say it if you don't want to. There's only 1 slot left for the m. 1 slot left for the m. Okay? And so it's essentially, I don't know, you have one set, you have 1 slot to put something in, and you have 1 thing to put there. It's equal to 1. 1 choose 1, I guess. I don't know. So the secret is, do you see there's a little bit of a pattern going on here? Well, let's just do this in total, I guess. Let's see here. How do I want to say this? Yeah, let's just unfold, I guess. Let's unfold this idea, and yeah, I think I can do that. So what is the formula for 11 choose 4? It's this big thing. 11 factorial over 4 factorial times 11 minus 4 factorial, which is 7 factorial. So, oops. This is all equal to 11 factorial over, that's just this part, 4 factorial times 11 minus 4 factorial, which is 7 factorial, right? And the next one is 7 factorial over 4 factorial times 7 minus 4 factorial, which is 3 factorial. And then this one is 3 factorial over 2 factorial times 3 minus 2 factorial, which is 1 factorial. 1 factorial. And then this one is 1 choose 1. Yay. Which is 1 factorial over, what is it? 1 factorial times 1 minus 1 factorial, which is 0 factorial. Times that. And actually 0 factorial, it is defined to be 1, so that's actually a valid thing to ask for. 0 factorial is 1, that's okay. And so this is just times 1 really, but that's the syntax. But watch what cancels. The 7s cancel, 7 factorials cancel, the 3 factorials cancel. The 1 factorials, in fact, cancel. And then the 0 goes away to 1. So really, the formula is 11 factorial, which was our original size of the string, over the different sizes of all of the different repeated letters, and then the last one wasn't repeated, so it was just 1 factorial, taken all to a factorial. So the secret is the number of distinct sequences with n1 ones, n2 character 2s, all the way to nk character k's is, where the total of all those characters is size n. It is your size, so n factorial, that's the 11 factorial, over how many repetitions you have. There are four i's, so over 4 factorial, times, there are 4 s's, times 4 factorial again. There are 2 p's, times 2 factorial, over, one more, right? One last slot for the m, it's 1 factorial. So it kind of goes away. And that's the general formula. So hopefully you see how these all cancel and they end up with that answer, but it's kind of cool. So if you just want to memorize this, I guess that works, but this is the intuition at least. That's why it works. All right. So with that in mind, here is a word for you to calculate all the permutations of. You have college. Please give that a try. Permute all the letters in the word college, and then here's this slide that you can stare at for a second to figure out how to do it. Maybe you want this one too. I don't know. All right. So first of all, how many characters are there? There are apparently 7 characters in this string, 7 slots to fill. And then how many duplicates are there? I think I see 2 L's and then 2 E's as well. So those are the duplicated letters. So without loss of generality, let's say that I want to place the L's first. I have 7 slots to fill in and 2 L's to place, so fill those in, please. And then I filled in 2 slots. I have to fill in the E's somewhere else, but I have 5 slots now left because I've placed the L's somewhere already. I have 5 slots now to fill with each of those 2 E's. And so that's what happens next. And then finally, I have C, O, and G left, and they're all just, they can go in any order. There's 3 different characters, and so there's 3 factorial ways to permute the rest of those. And that's equal to, of course, this same idea, all right? It is equal to, how many slots are there? So 7 factorial over, well, there's 2 duplicates for the L's, 2 factorial, and then there's 2 duplicates for the E's, so that's 2 factorial, and then there's 1 C, so 1 factorial times 1 factorial, there's 1 O times 1 factorial, and then there's 1 G, so times 1 factorial one last time. All right, that's all. So those are going to be equivalent, whichever way you want to think about it. They're both supposed to work. All right, let's see. I think there's just one last concept for the day, and that's to count what's called a multiset. So a multiset is when you do have a set that can have duplicates, and duplicates matter. The order of the duplicates don't matter, but you can at least have them. All right, so we consider the same kind of item in a multiset to be indistinguishable. So their order doesn't matter. So here is a multiset. It is 1, 2, 7, 7, 7, 7. It's keeping track of the fact you do have 4 different 7s. That's not the same. They can't you can't shrink that down to just the set 1, 2, 7 like you can with normal sets. This is a multi-set with duplicates. It's not equal to this multi-set. I hope you see that. And there are reasons to want to have multi-sets in math. It's so you can represent ideas like, I think you want a wallet with this multi-set of bills rather than forcing that to be the same as, oh, I just have 120. Right? So that's why multisets matter, and I would like to count multisets in a certain way. And usually our goal is, if you have an infinite supply of things, figure out how to fill a basket, like you have an Easter basket or something, and you'd like to fill it with, I don't know how to draw a basket. What does it look like? There it goes. You would like to fill it with n items from m varieties, where you can pick as many of each variety as you'd like. So how many ways can you do it all? So here we go. Here's an example where I'll show you the rest on the next slide though. Let's say that our basket, we can put dogs in our basket, and there are 4 breeds of dogs to choose from, and we can pick as many as we want of each. So let's say, like, I don't know, you can choose from, I don't know, you can choose some golden retrievers if you'd like. You can pick 10 golden retrievers if you want, but you got to pick 10 dogs from these 4 different breeds. Golden retriever, I don't know, Labrador Retriever, Chihuahua, and I don't know, Poodle, something like that. So you have 4 different things, 4 different places to choose from, and you can pick some Golden Retrievers, some Labs, some Chihuahuas, and then some Poodles, but it has to add up to 10. Did I already mess up? No. It has to add up to 10, though. And this kind of counting problem can be modeled with multi-sets. All right? So that's the goal, and here is the secret. Here's how you do it. Here's the secret to counting multi-sets. What you do is you imagine that each outcome, each possible multi-set you could make with like 4 Golden Retrievers and 3 Labs, etc. Imagine that each thing that you could make is a binary string. This is going to look really cool. Let me show you how that works for the dog example. So let's say that we have, again, 10 dogs to choose in total. Got to put them all in our basket. And 4 breeds to choose from. So there's that. And let's say that I would like to pick 3 Labs, or 3 Golden Retrievers, 3 Labs, how about 4 Labs? I don't know. And then, let's see, what was next? Chihuahuas. Let's say I want 2 Chihuahuas and 1 Poodle or something. I can represent the fact that I put, I want 3 of these, 4 of these, 2 of these, and 1 of these by putting them in order with 1s. This is a binary string, and then separating the breeds with 0s. Isn't that so cool? That's how you can represent the fact that I want 3 of the first thing, 4 of the second thing, 2 of the third thing, and 1 of the last thing. Isn't that neat? And if you wanted 0 of the last thing, you just don't put a 1 there. You will have had somewhere, somehow, you're going to put 10 1s, and all of the classes are going to be separated with 0s. Isn't that cool? So 0 is just the separator. And you can turn it now into a binary string counting problem. Isn't that fun? And so the way to choose 10 dogs, where you have 4 breeds to choose from, you want to count how many different ways can you make binary strings that look like this, that have a bunch of 1s and then 3 zeros. Really, all that matters is that you're writing how many characters total. Like the 1s plus, there's 10 1s and 3 zeros. You got 13 characters total that you want to count how many different ways there are to arrange. And then you have to separate always the 1s with 0s. And so really, all this boils down to is take a string of 10 1s, because you have to have 10 1s no matter what, and then just place the 0s somewhere. So it's really a game of where to place the 3 zeros. So how many ways are there to choose 10 dogs where there's 4 different breeds? 13 choose 3. That's pretty cool. So it's really equivalent to picking where you want the zeros to go in the string. This is the formula for it, but this is equivalent to picking where you want the zeros to go. Want the zeros to go in the string. There's nothing to do with the 1s. Like the 1s are forced. Like you're forced to have n 1s. As far as the formula is concerned, you're forced to have n 1s. But you have m varieties, and that means they need to be separated with m minus 1 zeros. And so it's really, the formula is n plus m minus 1. That's the 13. That's how many characters in your binary string. Choose m minus 1. That's where, so if you have 4 things to choose from, you only need 3 separators. So choose where you want those separators to go. That's how you can count how many ways to choose 10 dogs with 4 breeds. That's kind of cool, all right? And this is all, though, assuming you can take as much of each variety as you want, and each object of the same variety are indistinguishable. So, like, you can't differentiate between the Golden Retrievers. It's just like, I want this one and that one. There's no difference in the order or anything like that. So yeah, that's the dogs example. I guess I got ahead of myself. Sorry, I was going to explain it first, but no, I think it makes sense in this order anyway. So it's always about you're counting with you're counting subsets secretly. So we had n objects, that was 10 for our example, and then m varieties, which was 4 for our example. And so that became n plus m minus 1 over, or n plus m minus 1 choose, sorry, m minus 1. There we go. All right. Before we go, I would like you to try this, and this will be our last example for the day, just to remember everything. This one is not about multisets, it's just to make sure you were paying attention to the previous stuff. So, how many different strings of length 12 containing exactly 4 Bs can you choose over this alphabet, A, B, C, D? So your strings have to be of characters A, B, C, D, but you can only have 4 Bs. Like you can have, the rest can be all A's if you'd like, but these are your choices of characters and you're forced to have 4 Bs. See if you can figure that out. It's a good combination of some of the things that we were talking about. So, all right. Strings of length 12. So we know we have 12 slots to fill. You can label them 1, 2, 3, 4, all the way to 11 and 12. And then you have to have 4 Bs. You have to place the 4 Bs. So this is very similar to counting strings with duplicates. You got to pick 4 spots to place the Vs. Maybe here, 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 and here. How many ways are there to do that? It's like you got 12 options. You got to choose 4 indices to put the Bs in. And then the rest is fair game. You can put, after that, you can put them all, you can fill the rest of the slots with A's, you can fill the rest of the slot with some combination of A's, and C's and D's. You cannot choose B's anymore. Do you see that? Because you've already placed your 4 B's, you don't get any more B's. The rest is among the other 3 characters. So 3 characters that you can fill in the rest of the 8 slots. So it's 3 to the 8th power, because you can only choose A, C, and D for the rest of the slots. You've put your 4 Bs, can't have any more of those. All right, so that's going to be your answer, and I will box it for your convenience. So yeah, I hope that's what you figured out. That is a good practice of the kind of stuff that we learned today, and that is where I want to stop with this lecture. That is our introduction to counting. There's plenty more. It's kind of a different topic, I would say, but hopefully it's starting to make some room in your brain for itself. So yeah, that's all that I've got, and I will see you next time.